So good morning everyone once again and welcome to this lecture. In this lecture we will definitely be able to finish nuclear physics. We are doing the questions on activity and other questions. Let us move ahead and solve the next one. Now most of the questions in this category might have this ln and ln of or log of something coming, so you might not be able to solve the question to the last point, but we will be trying to solve the question as far as it is possible. Most of the questions that are going to come in exam will not be requiring this ln and log. It would be straightforward just like this. This is a question in from previous years, and it may have come many times again. The radioactive substance decays to 1/16th of its initial activity in 40 days. What is the half-life? I'll give you 2 minutes. Well, the correct answer is definitely 10. You can see it decays to 1/16th of its initial activity. So this activity becomes A0 divided by 16. You can write it as A0 divided by 2 raised to the power n, where n will be equal to 4. Number of half-lives is 4. 4 half-lives is 40. So 1 half-life would definitely be equal to 10. That is the answer that we are looking at. I hope you understand this. Let us move on to the next question. And the next question is like this. A sample of radioactive element has a mass 10 grams at an instant n is equal t is equal to 0. The approximate mass after 2 mean lives is I'll give you 2 minutes to solve this. The answer is definitely D. Well done. Now here we must use the formula m is equal to m naught e to the power minus lambda t. We just put the values and get the answer. M will be equal to m naught is 10 e to the power minus lambda. T is given as 2 mean lives. 2 mean lives means 2 by lambda. So it becomes 2 by lambda. So m becomes 10 e to the power of minus 2. So m becomes 10 divided by e square. In the question that you have in the exam, either the value of e or e square would be given to you, or you must know it, or the answer would be given in this form. In any ways, when you put down the values, you will get 1.35 grams. And that is the question. That is the answer that we are looking at. Well done. We are picking up good speed. Again, any one of this question, you will find them in your exam. In your next session, I will also do questions from the previous session. Just give me some time. Let me finish the quota that I have first. This is the next question. The half-life of AT-215 is 100 microseconds. Time taken for the radioactivity of the sample to decay to 1/16th of its initial value. And the answer is 1/16th of its original value. You have to reduce it. 1/16th of its original value means the number of half-life. 1/16th of its original value. So n will be equal to n naught divided by 16. So this will be n naught divided by 2 raised to the power 4. Number of half-lives is 4. So the answer is 100 multiplied by 4, and the time will be 400 microseconds. Do we understand this? Yes or no? No or yes? This is the next one in line. At any instant, the ratio of amount of radioactive substance is 2:1. If their half-life be respectively 12 and 16 hours after 2 days, what will be the ratio of the substance? So what is the answer for this question? We know that n is equal to n naught divided by 2 raised to the power of n. So it is directly proportional to the number of nuclei actually present and 2 raised to the power of n. So number of nucleus of 1 divided by number of nucleus of 2 will be n naught of 1 divided by n naught of 2 multiplied by 2 raised to the power of n2 divided by 2 raised to the power of n1, where n2 and n1 are the number of half-lives of the second and the first nucleus. n01 is in the ratio 2:1 and their half-lives are 12 and 16 hours. So in 2 days, how much would be that thing? We have to find out. So just so we multiply 2 raised to the power 2 raised to the power of number of half-lives of the second body, that will be equal to how much? 2 into 20, 2 into 24 divided by 16 divided by 2 into 12 divided by 16. And I think the answer that you are going to get is, oh, have I done it wrongly? And not half-lives I think you are going to get one by one. Are you getting it, or I have done something wrong here? N1 by N2 will be equal to N0 of 1 by 2 divided by 2 raised to the power of N. I am not getting 1 by 1 from here. I think I am going to get 4:1. Maybe something wrong with my calculations, I think. 2, 8, this will come 3. I think I am doing a mistake over here, or maybe the answer that is given may not be correct, but this is what we should get. N1 is the number of half-lives of the first, and N2 will be the number of half-lives. Let me just calculate N1 and N2 here. Maybe I'm doing a mistake here. N1, the number of half-lives, the total number of hours in 2 days is 2 into 24 divided by 12. So the number of half-lives of this will be 4. No, I'm doing it correctly. And number of half-lives of this will be, why I have written 12? I should have written 24. That 12 created a confusion in my head. Number of half-lives of this would be equal to 3. So it will be 2 raised to the power 3. 2 raised to the power 3 divided by 2 raised to the power 4. So the answer will be 1:1. I got confused. I always get confused in multiplication and division. I don't know. This is one of the things that is very hard for me. Anyways, let us move on to the next thing and the next heading. And the next question is this: from a newly formed radioactive substance, half life is 2 hours. The intensity of radiation is 64 times the permissible safe level. The minimum time after which it can be safely taken from its source is. So, what is that you have to see? This question is just given in the reverse way. It is given that the intensity of radiation is 64 times the permissible level. So, basically, the activity is 64 times more than the original value, than the value which is safe, than the value which is safe. So, the minimum time after which it will be safe to work from this source, it is now 64 times. So, it has to become 1 by 64 times of the original. So, A by A naught should become 1 by 64. Now, it will be safe. Now, 64 can be written as 2 raised to the power of 6. So, the number of half-lives that has to go will be 6. So, how much time it will take? 6 into 2, 12 hours it should take, where the intensity will become permissible. It will become 1 by 64 of the intensity which is there right now, and therefore the permissible time after which you can work there is 12 hours. Are you able to understand this? Yes or no? Remember the different ways in which the same question can be asked. This is another way in which the same question can be asked. The counting rate observed from a radioactive source at 0 seconds was 1600 counts per second, and at 8 seconds it was 100 counts per second. The counting rate observed as count per second at t is equal to 6 seconds would be how much? Now, counting rate, you can call it as activity. At time t is equal to 0, it was 1600. At time t is equal to 8 seconds, it becomes 100. As you can see, it becomes 1 by 16 times. So, activity becomes A naught by 16. That will be A naught divided by 2 raised to the power of 4. So, the number of half-lives is 4 and time it takes is 8 seconds. So from there you can find out the half-life would be 8 divided by 4, 8 seconds divided 8 seconds divided by 4. The half-life would be 2 seconds. You have to find the activity after 6 seconds. In 6 seconds, the number of half-lives n1 would be equal to 3. So activity will be equal to A naught divided by 2 raised to the power of n, 1600 divided by 2 raised to the power of 3, 1600 divided by 8, and your answer should be somewhere around 200. I hope everyone is getting this. Yes or no? I'm trying to cover all types of questions that are possible to come. This is the next type which should come. Half-life of a substance is 20 minutes. What is the time between 33% decay and 67% decay? So how are we supposed to find this? The first case is given when it has decayed 33%, and the second case it has decayed by 67%. So number of nucleus left in the first case will be 0.67 times of n naught, because 33% has decayed. In the second case, the number of nucleus left will be 0.33 times of n naught. Do we understand this? Well, you can see that this n2 is approximately equal to n1 by 2. Yes or no? This n2, the number of nucleus that is left after 67% of decay is approximately equal to n1 by 2. Now you can think it of in this way, that I started with n1 number of nuclei, and now the number of nuclei is n1 by 2. It has become half. How much time would have gone? The time that would have gone would be 20 minutes, which is the half-life. Because between 33% decay to 67% decay, the number of nuclear become half, and after every half-life, the number of nuclear become half. So this is very one important question that you can remember. I hope you understand this. Yes or no? No or yes? Now let us come to this one. Anyone has noted down the previous one? Okay. This is the next one. The fraction of atom of a radioactive element that decays in 6 days is 7 by 8. The fraction that decays in 10 days would be how much? Well done. 31 by 32 is the answer. Again, this question is given in a roundabout way. It is given that the number of radioactive element that has decayed is 7 by 8. So the number that is remaining will be 1 by 8 and not by 8. From here you can get the number of half-lives as 3. 3 half-lives is 6 days. So half-life become 2 days. In 10 days, the number of half-lives N1 will be equal to 5. The number that remains will be N0 divided by the finger stopped. The number that remains will be N0 divided by 2 raised to the power 5. 2 raised to the power 5 is 32. So the number that remains is N0 by 32. And therefore, the number that has decayed will be N0 minus N0 by 32. It will be 31 N0 by 32. I hope everyone has understood this. Let me get the screen on. So the number that remains will be N0 divided by 2 raised to the power 5, N0 divided by 32. So the number that has decayed is 31 by 32 into N0. Everyone understands this? So remember, whatever way the question is asked, the question can be solved in this particular fashion. We'll do more questions, but let us just finish 2 or 3 small things before we get on to the previous year questions. The next thing that we are going to do is sometimes known as parallel radioactive disintegration. Parallel radioactive disintegration. Now, what do you mean by this parallel radioactive disintegration? Now, sometimes a radioactive particle can decay simultaneously by 2 processes. So it can decay by 2 processes. It can decay by alpha decay. At the same time, some nucleus may be decaying by beta decay. A single nucleus cannot decay simultaneously by alpha and beta. But if you have a sample, some nucleus may be decaying by alpha, some may be decaying by beta process. So this A nuclei sample, it may be decaying by alpha decay and giving us B. Some nuclei may be decaying by beta process and they may be giving us C. This is known as simultaneous decay. Do we understand simultaneous decay or parallel decay? So if you have such type of decay, some nucleus are decaying by process 1, some nucleus are decaying by process 2. So at any time, the total number of nuclei initially present will be equal to Na plus Nb plus Nc. Don't have to remember all these things, they might not be asked, but this is just for your knowledge. They might ask a part of this. So the rate of decay of A will be equal to minus of rate of formation of B and C. Now remember, the rate of formation of B will be minus lambda into lambda 1 into number of molecules of A. Similarly, rate of formation of C would be equal to minus lambda 2 times Na. I hope you are understanding this. From here, you would be able to find out or derive this very important and very simple result, that rate of decay of A can be written as minus lambda 1 plus lambda 2 times A, or I can say that for this process the effective lambda can be written as lambda 1 plus lambda 2, and the effective half-life can be written as T1 T2 upon T1 plus T2. Do we understand this? Instead of writing it as T1 T2 upon T1 plus T2, you can also write it as 1 by T half. 1 by T half will be equal to 1 by T1 plus 1 by T2. You have to remember this. This is a very important result that will help you in solving some questions which may be only coming in JEE Advanced. I'll give you a minute to note this down. Now let us move to this simple question. And the question is very simply, the mean half-life, not the mean half-life, the mean lives of a radioactive substance for alpha and beta emissions are 1620 and 405 years respectively. By how much time will the activity be reduced to 1/4? So it is decaying by two processes. So lambda will be equal to lambda of alpha plus lambda of beta. Mean life is given to you, so you can find out the lambda from here. That will be equal to 1 by 1620, which is a lambda for alpha decay, plus 1 by 405. Again, you need to calculate this. The answer that I have is 1 by 324. I think 1620 is 4 times 405. From there you get 1 by 324. That is lambda. That is lambda. Now you want the activity to be reduced to 1 by 4. You want the activity to be reduced to 1 by 4. So the number of half-lives would be 2. So time will be equal to 2 multiplied by the half-life. Half-life. Half-life is 0.693 divided by lambda. So 2 multiplied by 0.693 divided by lambda, and 1 by lambda is 324. So this will be 2 multiplied by 324 multiplied by 0.693. Again, it requires some calculation, but after calculation, you should end up with 449 years. And that is the answer. I'll give you a minute to note this down. Then you move on to the next heading, the last heading for this chapter, which is successive disintegration. Now, there is one radioactive nucleus A. It disintegrates into B, but B may also be radioactive, so it will disintegrate into C. Let us say that lambda 1 is the decay constant for conversion of A into B, and lambda 2 is the decay constant for conversion of B into C. So the rate of disintegration of A, which will be also equal to the rate of formation of B, will be equal to dN by dt, which will be equal to minus lambda 1 into N1. What do you mean by N1 here? N1 is the number of, if I write initially, at time t is equal to 0, at time t is equal to 0, let me write it here, at time t is equal to 0, this is N0, this is 0, and this is 0. At any given time t, the number of molecules of A is N1, the number of molecules of B is N2, the number of molecules of C is N3. I hope you understand this. The rate of disintegration of B will again be equal to the rate of formation of C. The net rate of formation of B will be equal to rate of disintegration of A minus rate of disintegration of B. Do we understand this? Please raise your hands so that I can understand that you are able to understand this. Just give it time. So basically what I am doing here, at time t is equal to 0, the number of molecules of A is N0. At any time t, it is N1. For B, it is 0 and N2. For C, it is 0 and N3. Writing all these equations, I can write, you just need to write this equation. You will not get time to solve them, and they will not be asking you to solve this equation. I will give the result. N1 will be equal to N0 into e to the power minus lambda 1t. I hope you understand this. This is the rate of disintegration of A. Now to write the value of B, N2. Let me first write the rate dN2 by dt will be equal to lambda 1 N1 minus lambda 2 N2. I hope you understand this. Everyone? Everyone understands this? And to write the equation of the third one, rate of formation of N3 dN3 by dt will be equal to minus lambda 2 into N2. Do we understand this? Yes or no, everyone? I'll give you 2 minutes to note this down. Now solving these linear equations, solving this differential equation, you will get the value of n1, n2 and n3 as a function of time. Don't have to solve this, you just have to remember n1. n1 is straight away coming from the original number of a. So n1 will be equal to n0 into e to the power minus lambda t. To get the value of n2, this is the formula for n2. You just have to remember this. This question can only come in JEE Advanced. There is not a very simple formula to calculate the value of n3. So how do you get the value of n3? You get the value of n3 from this formula. N3 will be equal to n0, the original, minus, you know the value of n1, you know the value of n2, you will get the value of n3. Do we understand this, everyone? I'll give you 2 minutes to note this down. This is the last heading of this chapter. We call it radioactive equilibrium. In a radioactivity series, you can see that a radioactive nuclei will decay into other radioactive nuclei, and this might decay into other nuclei. If the rate of production of one radioactive nuclei is equal to the rate of decay, the rate at which one is forming is same as the rate at which one is decaying, you will have an equilibrium, and the number of the nuclei of that particular substance will remain same. The equation will be lambda 1 into n1 will be equal to lambda 2 into n2. Lambda 1 n1 is the rate of formation. Lambda 2 is the rate of decay. If these two rates are same, that means lambda 1 by lambda 2 is equal to n. Lambda 1 by lambda 2 is n2 by n1, t half 2 divided by t half 1. We will have the condition of radioactive equilibrium. I'll give you a minute to note this down. That takes us to the last part, and this is the radioactive series. As I told you, when a radioactive nucleus decays, it may not yield a stable nuclei in just one disintegration. It may keep on disintegrating, and at the end of the chain, you will get a stable nucleus. There are 4 radioactive series that we have found out. The first one is known as 4n, then 4n plus 1, 4n plus 2, and 4n plus 3. 4n series, just for your academic purpose, just write them quickly. Starts from thorium 23290 and ends at lead Pb 20882. Then value of n is 52. Alpha particles are 6. Beta particles are 4. Then we have neptunium series, uranium series, actinium series, starting from all these unstable nuclei and ending up with stable nuclei. As you can see, all of these series are ending up either at lead or bismuth. Give you a minute to note this down. Do it fast if you want to. Just an example of one of the series, the uranium series. Don't have to write it down. It starts at uranium, that is the first nucleus, and you can see it ends at lead by alpha beta particles. This is how the series goes. Don't have to note them down. This is just for your academic purpose. Let me just move ahead and solve some questions. And this is the first one that you are going to take from your previous year papers. This is from January attempt. 29 January shift 2, and I'll give you 2 minutes to solve this. So what is the answer? The answer is 8. Ratio of their number of A divided by number of B will be equal to n naught. You have to find the value of n naught here. In first case, the n naught is 20. In second case, the value of n naught is 10, 20 by 10. into number of half-lives of the second. Number of half-lives of second is 2. Number of half-life of the first, sorry, number of half-life of the second one is 4, 2 days. Number of half-life is 1. So this is number of half-lives of, again I make mistakes in this calculations. Number of half-life of the second one is 4. Number of half-life of the first one is 2. Multiply, divide it, and I think you will get 8. The ratio is 8:1. Do we understand this, everyone? Everyone is able to make this out? Yes or no? No, yes? Now remember, these are the type of questions that are coming. This was the question from your attempt that you gave. This was a question from 2022. As you can see, the question is practically same. I'll give you a minute to solve this one. So the answer is how are we supposed to do this? 8:1, same thing. N is equal to N naught divided by 2 raised to the power N. Originally have N1 and N2 nucleus, half-life of X is half to that of Y. After 3 half-lives of Y, the nucleus are equal. So N1 dash becomes, sorry, not N1. N1, the number of nuclei becomes N2. N1 dash becomes equal to N1, N2 dash. So N1 divided by 2 raised to the power of N1 will be equal to N2 divided by 2 raised to the power of N2. You have to find the number of half-lives that has happened. 3 half-lives of Y, and how many half-lives of X you will have. You will just have to find it out. Find out the ratio, and I think you will get the answer as 8/1. Everyone got this answer, yes or no? Let me move on to the next thing. Sometimes I have seen question coming on this particular thing, which is nuclear fission. Don't get confused if you get a question like this. Now, what happens in nuclear fission is that you normally have an equation. Normally, nuclear fission is done on uranium U-235. It is bombarded with 1 neutron, and you have some resultant that you get. And the energy that is released in if one nucleus of U-235 is bombarded, the energy release is tremendous, 200 mega electron volt. Larger nucleus gets broken into smaller one. The energy release is always given for one particular nucleus. For one nucleus, this much energy is released. If a question comes, you can find out how much energy is released by finding out how many nucleons, how many nucleus are undergoing fission. So just note this down. Nuclear fission is just a process in which a heavier nucleus gets converted into lighter nucleus and it releases energy. The energy release is always per reaction or per nucleus. If one nucleus gets converted, how much energy is released? So if any question comes, you can solve it from this data. I hope you have noted it down. Well, you can solve this question, and remember, it's a simple question. This is taken from your 2023 paper. Which date is not mentioned in this paper. So when X240Z nucleus goes for fission, the energy release is 200 mega electron volt. Calculate the energy released when 180 grams of this sample undergoes fission. I will give you 2 minutes to solve this. And I have an answer 6.022. That is correct. So remember, when one nucleus undergoes fission, you have 200 mega electron volt. So just have to find out the number of nucleus, the number of moles. You have 120 grams, 240 is the mass number. So the number of moles is 2. So the number of nucleus will be 2 into Avogadro number. So the total energy will be 2 into Avogadro number. You can take Avogadro number as 6 into 10 raised to the power 23 multiplied by 200. The number of moles is not 2, it is 1 by 2. It was 120 grams of sample. So this must be equal to 6 into 10 raised to the power 23 into 200 divided by 2. So the answer is 6 into 10 raised to the power 25 mega electron volts. Do we understand how questions of this type are done? See, the questions are pretty damn simple. And you can easily solve them. This is a question again from, let me take a question from your attempt. This is 29th of January, shift 1 paper. And you can see the questions that are coming are pretty straightforward. A nucleus 23692 undergoes 2 alpha and 1 beta. Find the atomic and the mass number. I'll give you a minute to solve this. So, what will be the answer? It goes 2 alpha decay. From there only you can get the answer. Here Z is misprinted. It should be equal to A. They've written it as Z. The mass number can only change by alpha decay. The mass number will change by 4 into 2, 8. The only option that matches is option C. So my dear friends, option C is the correct answer for this one. I hope you have understood this. Let me move on to the next question. This is from 2022 paper. A radioactive sample is undergoing alpha decay. At time T1, the activity is A, and at time T2, the activity is A by 5. What is the average lifetime? Its activity is A after time, at time T1, the activity is A. So I can write A as A naught e to the power minus lambda T1. And you can write A by 5 as A naught e to the power minus lambda T2. When you divide, if you divide 1 by 2, I think what you are going to get is 5 will be equal to A naught will get cancelled, my dear friends. E to the power lambda times, I think you will get T2 minus T1. If I am not correct, I am very bad with divisions. So lambda will be equal to ln of 5 divided by T2 minus T1. Therefore, the average life is 1 by lambda. And the answer that you should be getting, my dear friends, is option 3, T2 minus T1 divided by ln 5. I'll give you a minute to note this down. I hope you have noted it down, yes or no? Now, this is a question from your 25 January shift 2 paper. Similar question I think we had done. All right. Probably skipped it at that point in time. A stationary nucleus breaks into two daughter nucleus having velocity 3:2. What is the radius of the nucleus sizes? What is the radius of their nuclear sizes? This is 25th January, shift 2. So the stationary nucleus breaks into two daughter nucleus. The nucleus is stationary, so the law of conservation of momentum should hold m1 into v1. The momentum of the first one should be equal to m2 into v2. So from here I can say m1 by m2 will be equal to v2 by v1. m1 by m2 will be equal to v2 by v1, and v2 by v1 will be equal to 2 by 3. This mass, the ratio of their masses will be equal to the ratio of their mass numbers. So I can say a1 by a2 will be equal to 2 by 3, and you must know radius r1 by r2 was a1 by a2 raised to the power of 1 by 3, and therefore my dear friends the answer is 2 by 3 raised to the power of 1 by 3. I hope you have understood this. I'll give you a minute to note this down. All these things we have already done, and the only thing that you have to remember is to remember things, and the only thing you have to forget is the habit of forgetting things which you are not able to do even till now. Anyways, I have to move ahead in life. This is a similar question to what we have done. This is from the paper of 2022. A radioactive material decays by simultaneously emission of two particles with half-life of 1400 and 700 years. What will be the time after which one-third of the material remains ln of 3 is given as 1.1? So how you need to solve this? You need to find out the lambda effective, lambda alpha plus lambda beta. So you can write it as ln2 0.693 divided by 1400 plus 1 by 700. So from here you will get it as 3 by 1400 multiplied by 0.693. Now the activity of the sample should become 1 by 3. So n, which is equal to n naught by 3, should be equal to n naught e to the power minus lambda into t. So if I take ln, I will get ln of 1 by 3 will be equal to e naught, e naught will go away now, will be equal to minus lambda t. From here, I will get the value of t, and the value of t that we are getting from this equation is coming as approximately equal to 740 years by putting the value of ln3 as 1.1. I'll give you a minute to note this down. That takes us to the last question of this class, this particular topic, and this is from your JEE Main of 2023, 31st January, shift 1. A neutron will break into proton, but proton will not break into neutron, because a neutron can on its own break into proton, but a proton on its own cannot become a neutron. Why? What is the answer for this one? This is just a theoretical question based on whatever we have discussed. This is a culmination, a very good culmination of what we have discussed in the entire class. And the answer is? And the answer is definitely option B. Rest mass of neutron is greater than the rest mass of proton. Therefore, this will be an exothermic reaction. It can happen on its own. The binding, the Q value will be positive, and therefore this reaction can happen on its own. With this, we have come to an end of today's class and this particular topic, nuclear physics. We are done with this nuclear physics once and for all. In the next class, we'll start with your last topic, so-called last topic of modern physics. We'll start with semiconductors. I hope you have enjoyed this class and you have studied and you have understood this. If there's any problem, come back to me. Else, I will see you tomorrow with the next topic, semiconductors. Take care. Bye bye.